Thanks for your patience. I think we're almost there.
It's not at the Venture Cafe is having in-person meeting again. Remember those, John? The Venture Cafe?
Yeah.
I guess last time I went to 500 people. I know, it's probably, it's a thousand. Good, only a trillion? Yeah, I don't think Sloan School will do that at all. They won't do it for BLU. And I thought those guys were grandfathers. So I don't know. We'll have to figure something out. I mean, we're almost past it here.
There's always something, isn't there? Well, supposedly we're live, but I can't find it.
You see if you're live?
No, so I am, okay, I see. It's on a different link. All right, well. All right, well, go ahead and get started. We're running now.
All right, hey everyone. So before I get started, I just want to say that I'm really excited that we can have these again in person. This was one of my favorite things that I attended before COVID started. It's been about 2 years since the last one. So this is good. Hopefully we can come to more of these as well. Thanks to you guys for hosting us. So for those who don't know me, my name is Benjamin. I've done a couple of these before for the HPC and GPU Supercomputing group. I'm currently the president of the HPC club, but also hi to everyone watching for the live stream. So I serve as the president of the HPC club. I've been part of the club for about 3 years now. This is my last year because I'm graduating this semester. So getting to do this before I graduate after COVID has been pretty cool. So for this talk that we have prepared, Tara and I are going to talk about our club. We're going to talk about the SC student cluster competitions at the SC conference. So I'll start off and then Tara will take over for the competition side of things because I won't be so let's get started. So we have 4 Vijay Thakkar today. The first is going to be the state of HPC clubs, our club, as well as just clubs in the Boston area in general. Then we're going to talk a little bit about the HPC history, the stuff that we've been doing. We also dug up a couple of old photos that we thought might be good to look at as well. Next will be the SC20, SC21 competitions that we've participated in. And then finally, we'll talk about our participation at this upcoming year's student cluster competition at SC22 and our plans for that. If you have any questions at any time, just jump in. So first, state of HPU, HPC, and HPC clubs in Boston. Recently, we made a lot of progress with our club. I guess it's no secret that HPC clubs within the Boston schools have grown in number recently. I think Northeastern had a club for a while, Lowell, but over the years, HPC is like a very small but still tiny community. So I'm really happy that our club at least has grown in number. We've also been doing a lot of university collaboration with universities around the Boston area. For example, MIT, Northeastern, UMass Lowell, I'll talk about all those later. And then we also have an in-house cluster that I would like to highlight, which has been an ongoing project for a couple of years now. So as far as school outreach goes, so we have done partnerships for events and for competitions with some of the schools that I've highlighted here. Last year, actually, we did the SC competition with UMass Lowell as well as Boston College, and it was actually Boston College's first time participating or having a representative at the competition, which I think is cool, bringing new schools. So that was part of a Massachusetts Green Team collaboration that we did. We revived the collaboration between the Boston teams that had kind of died out there for a couple of years. And then, as always, we collaborate with MIT through Kurt himself. And we actually recently got in touch with one of the current PhD student at MIT who used to run the Machine Quad team at these student cluster competitions. For those who don't know, Machine Quad has been like a dominating player within the student cluster competitions. I think they actually have a record for having won the most. So we want to set up a 30-minute meeting with him whenever he's got time. Pick his brain for some competition tips and tricks that he'd be willing to share. And it'd be a really cool way to also interact with the MIT student body. So the next thing I want to talk about is our in-house cluster. It is our own computing cluster, so BU-HPC owns the entirety of it. Currently, it resides in the IT room within BU. So the cluster, we call it the Baker's Dozen. And it is composed of 10 Raspberry Pi 4Bs, as well as 4 NVIDIA Jetson Nano processors. We got these a couple years ago, thank God, otherwise it'd be so much more expensive now. But we call it the Baker's Dozen because one of these nodes serves as the head node, so one of the Raspberry Pis. And then the rest is 13 of them, right? So Baker's Dozen is 13. And we have a couple of uses for them that we keep them on board for. One of them being club workshops. So we have a model currently where in the fall we host workshops for our club for new students who are interested in learning about HPC and its related technologies. So for example, a couple of those were we did a benchmarking workshop where we used high performance LinPack, and people got to try running their configurations on the cluster, as well as we use them for parallel programming with OpenMP, some workshops there. And then we also use it for competition practice. Specifically with any other understudies that we have. We can work off of our Azure clusters while they work off of the Baker's Dozen cluster. And then I had a couple pictures that I wanted to show. So the one over here on your left, this is when we first got the cluster. So everything's such a mess on the floor. You can see that we basically buy all the components, the Raspberry Pis, all of the USB connectors, Ethernet cables, all of that. It costs us around $800 per month. And then this is it all set up. We took this picture pretty recently. Currently, we actually have 2 cluster teams or cluster management teams that are working on these clusters right now. So for the Raspberry Pi, we have David and Schaumburg in the back that are on the clusters, as well as another member, I think, Grant, who's on here right now. And then these Jetson Nanos, they're being managed by Emeka as well as Raina's under right now. So yeah, there's a lot of club integration going on. We have a lot of things going on at once, projects this semester. So club activities have gone together. Okay, so let's move on into HPC history. Just after some interesting things to talk about here. So we'll start with we'll split this into 2 sections. The early days of HPC, around the years of 2011 to 2016, back when we weren't still a confirmed club. And then we'll take a look at one once we became a club within VU. So on the top left here, I did this search up on our Twitter. You may have heard about VU's Jetson TX cluster at I think it was ISC 16 or ISC 15. And this is a pretty weird architecture that we bought because these are ARM chips. And this is actually still being referenced today. This is a news article from HPC Wire for the SC21 competition that we attended. And you see they talk about how we've been known for using innovative hardware approaches. For example, the Jetson GPUs. So we like to think of ourselves as a team that has weird, innovative approaches to these competitions. And then two more items that we got that we found recently is the first prize plaque from the ASC Student Cluster Competition. This is from a team a long time ago. I don't know any of the people on the so people are listed if you can't see underneath the team name. I don't know anyone there except for Kurt.
Things like yesterday.
Yeah.
And accompanying that is the trophy that they won at ASC for that year. So that's that part of topic sessions. And then moving on to the present, this is like 2018 to about now. At one point, Natasha, the previous president of the club, was actually asked to give a keynote presentation about parallel programming to the Boston hackathon. So Tucker in 2019, UCN conference presenting on hackers guide to parallel programming, one of our core workshops. So that's pretty cool. Here is me and Quentin, our OVP. This is when we were first setting up the Pi cluster, and you see we're discussing what the hosting should be for the cluster nodes. We ended up settling on UHPC slice whatever, because the guy's pretty biased and it just doesn't. We thought it was pretty big for the cluster. And then a little more towards the recent present. We had our first virtual general meeting. So there's a picture of it. So in our struggling, we get Zoom working for our first general meeting, but things ended up going pretty well. So you can see that on the top left right there. Some of the eBoy that I've already previously graduated that I don't think anyone here really got to meet are Yuja. She's a biomedical engineer. She's at Rice University right now for a PhD. And then Parker on this call. That's called. Norman, who was co-president with me a couple of years ago. Right now he's at Apple. I say Parker. In the middle here, this is one of the recent talks that we gave to the HPC Club. So this is on CPU architecture. Mike Klein, our current treasurer, is providing a play-by-play commentary to the fierce battle between x86 and ARM. And then on the right side over here, this was another recent workshop, Intro to OpenMP led by Carl Knox, teaching members how to use OpenMP to speed up algorithms. So towards the end of last semester, we actually had a club outing, which was great. Got to know some of the members more in depth. So we celebrated the end of the fall 2021 semester at Fire and Ice. And pictured from left to right are the club members Howie, Richard, Vance, Henry, and David. In the middle here is this recent Splash 2.0, which is BU's kind of club fair. So we shared a table with the IEEE club. And we're being pilot table books. And then finally, cluster management. So this is Emeka and Raina setting up firewall rules on our Jetson Nanos during a cluster management meeting. So that's a little taste of what HPC does as a club. Okay, and I guess now I'll turn it over to Howie for the rest of the presentation. Thank you, everyone.
Yeah, thanks, Matt. Yeah, so like you mentioned, to graduate this year, so I'll be taking over the competition team. Okay, so for starter, so in this next section, I want to talk a little bit about SC20 and SC21. So what we did in the previous 2 years as a competition team, as well as our new plans for the next competition. So for starter, the student class competition is a 72-hour annual event at the Supercomputing conference where the committee invites universities from around the world to build an HPC cluster and optimize some of the programs that are run in the national labs or HPC industry, as well as some of the benchmarks. There was a period of time between like 2018 and 2020 when Boston was sort of out of the competition scene. Until 2 years ago, in SE20, we were very, very fortunate to be accepted into the competitions. And that was actually where I met Ben for the first time. So for the SE20 competitions, there was 6 of us from the HPC club. We're all the biggest equal members. But back in 2020, I was a freshman in college, and it was one of the first time I ever touched a large scale compute cluster. And in addition to that, because of COVID, everything was moved to virtual cloud. So usually for the competition, you would go there in the competition floor and actually set up the hardware for yourself as well as the software stack. So we also have to navigate with working with an Azure service, which is on top. So that just adds additional complexity to the preparation of the team. So with our experiences and having to adapt to different technologies, we didn't do that well that year. So if you look at the slides, there are 4 different competition categories. There's CSM, which was a weather simulator, and it was GROMAX, which was a molecular dynamics simulator, and the reproducibility challenge was a material science paper. So for the reproducibility challenge, you have to try to recreate some of the experimental results that the author got in their paper. And for the mystery application that year, it was a graph analytic algorithm. Although one thing we were pretty good at was running benchmarks. We got about like 64 teraflops on our CPU cluster on the Azure service. So immediately after the competitions, me, Ben, and Kurt, we started talking about how we can do better in the 2021 competitions. And one thing we realized is that we really need to like start early with these kind of things. So we began preparing since November 2020, which is immediately after. We started reaching out to different schools in the area to see if they want to participate in this collaboration effort. So as Ben had mentioned earlier, in the early days, we used to compete as the Massachusetts Green Team. So we really want to bring back this consortium between different greater Boston college schools. So we went as the Massachusetts Green Team once again in SE20. It was 4 of us from BU, Richard from BU Maxwell, and David from Boston College. And we met throughout the summer to get started early and try to get things right a full month before we actually have to do the competitions. And that did to improve, and that turned out to be a really effective strategies. For the competition, we ended up getting first overall benchmarking in the US and 3rd overall benchmarking on all the competition teams. And we had this one goal, for the competition, which was to be able to complete all the challenges that we were given. And we did exactly that, which I'm really proud of. So next slide. So this brings me to the next point, which is SE22. So today is April 5th, meaning that we got about like 3.5 weeks until we have to submit the application for SE22. And we actually started preparing for that already. So SE22 is going to take place in Texas this year. And it's going to be the first time in 2 years that we don't have to do things on the cloud anymore, which could be a double-edged sword because in the past 2 years we've been only working on cloud service. So now we have to change our strategy to think about how we can actually maintain the hardware as well as the software. And they actually just announced the application recently. So the first application that we have is called PASTA, which is like a fluid dynamic simulation. And the other one is Max, which is a molecular dynamic simulator as well. So we would like to actually expand our invitations to not just BU students, but to students from different universities in Boston areas. We currently have 2 open spots on the team, and we're hoping to get the final team composed by April 15th. And if you're interested about this, please feel free to reach out to me by email, or you can fill this form. Or if you just want to be under study, you're also welcome to join us in our meetings. So that's at the end of the presentations, and we're going to be taking some questions to get everything. I'm going to read the slides here. So yeah, thank you everyone for
that laptop for the Zoom portion? Then, yeah, if the Zoom link is on the meetup page,
Yeah.
because Elizabeth Lee wants to talk real quick, but,
Yeah.
you suppose there'll be, feedback?
We'll find out.
We will find out.
This is my first attempt at this, so it's a little bumpy.
So if it isn't passing the audio, which is possible, we'll just turn off the, yeah, so. Yeah, go to that, and then, go all the way down to the bottom of the comments. Okay. If you share the screen, it won't get the video feedback, right? Go back. Sure. You online, you can tell her.
Elizabeth, if you can hear us, if you want to come off mute, I think we can hear your question.
She can share the screen too.
Yeah, if you have a screen to share, Elizabeth, I can let you.
Hi,
Hi there.
how are you doing?
All right, I think we can hear you.
Yes.
Good.
Are you ready for me?
Go for it.
Ah! How's everybody doing? How many do you have in the audience?
23, 24.
Wonderful.
Yeah.
Great. Well, how much time do I have, Elliot?
Well, I don't know. Do you have a proper presentation? We can try and get you set up better.
Yes, 39.
I have a
30.
very improper presentation. My presentation is improper, but I will share my screen.
If you don't mind, that'd probably be a little better for folks. Yeah.
I think so.
We're going to try and get your audio passed through a little better, Elizabeth.
Okay.
If you want to keep talking, Elizabeth, we'll see if this is working.
Okay, I'm Elizabeth Leek. I am Director of Research Computing at Boise State University. I'm actually joining you from Iowa. I recently joined Boise State. I was at Iowa, University of Iowa. I am the co-chair for the Practice and Experience in Advanced Research Computing student program. We have a deadline coming up May 1st. And I would like to encourage everyone to apply. And we do actually, whether or not you're funded to attend. Now, some people have internships. If you have an internship, my recommendation is to talk to your internship coordinator and ask if they have support for you to attend. And sometimes you'll be surprised. They might just send you to PERC because it's a great place to learn the skills that you need to succeed on the job. But I've just pulled up the webpage for PERC 22 and the student program. You can find it from the drop down here. Apply by May 1st. We may extend that depending on how many we get in. Are you able to find me on the screen yet?
I'm pretty sure we can see you.
Okay,
Yeah.
I see a blank
Yeah.
screen.
And we can hear you.
right. Good. All right, so the elements of the student program include an orientation and welcome on Sunday. And at that, you'll get your bearings. You'll learn a little bit more about the technical program and what's the offerings of the student program itself. And we plan the student program so that it is around the rest of the conference. So students are free to go attend all of the sessions. And if they receive financial support from the conference, they are required to participate all week. So you can't just drop in for one day. But we do have a technical program, a student volunteer program, resume clinic, and pitch it workshop. And for the second year, we'll feature the internship spotlight, which is really cool. Last year we did this, and it was the first time for PERC 21, but we called interns from across the country and interviewed them. And I made these little tiles to promote it, but then they each showcased their experience with I think we had like an 1.5-hour presentation by all of these interns. Some of them were funded under the Exceed Empower program. I think their Empower's last cohort is already funded for summer, but they're going to be attending. So you'll hear about the places where they worked, the type of skills they needed for their jobs at national labs, in various places. Ariana Martin, I think Ariana has an internship this summer with British Petroleum, and Ariana will be at PERC 22. Her employer is actually sending her, underwriting her whole trip. Christopher Sherrill had a physics internship. Jamil was at University of Iowa. He was actually worked with me there. And again, you can visit this website and see all these wonderful internships, because a lot of times students don't realize what's available out there by way of internships. But because the field of high performance computing and data science is so rapidly changing, it's rare that students get the training and the skills they need for the workplace at their universities. It's very rare, unless you have a big research center on your campus. But this gives you some insight as to what's available at the national labs and other places you might not think about looking for work. And the student mentor program is really fun. We have a mentor dinner where the mentors and proteges get to have dinner together. And we take great pains to pair students with mentors who are experienced in the field that the student's interested in pursuing. And often I will hear after this event that they've changed their mind about their trajectory. They want to pursue something different because of someone they met at this conference. There's an exhibitor, I call it speed dating, Q&A. It's a speed networking event where after you learn how to develop your elevator pitch and your resume building workshop, you go to the exhibitor Q&A speed networking event, and you meet with the sponsors who are actually underwriting the cost of the conference, because they're all headhunting and they're all looking for fresh talent. So it's a good place to meet the representatives and see if you can get a sense for the culture represented by their firms, their organizations. And for the first time, Kurt, we need a drum roll. Introducing the Village. The Village will be a tabling event where each table will feature a different competition model, so a training model. And this has been difficult to execute without knowing who we were going to have there. So it's kind of like build it and they will come. If the students show up with experience, I saw a presentation on SC student cluster competition. I'm a judge for the ISC student cluster competition. I was involved with India SCC last year. So I know everybody that comes will have different experience. We have on our student program committee, we have representation from the hackathon that usually is co-located at PERC every year. There's a cybersecurity penetration testing program at Temple University. Anshul Regge leads that, and she's on our team as well. So we're waiting to see who applies, and then if you come in with experience on a particular model, then you'll have time at your table and you can tell about your experience with that cluster competition or whatever. And we'll encourage you to make a poster and display that all week in the village. So again, please apply by May 1st. If you have questions, you can write to perk22students@gmail.com. And otherwise, we hope to see everyone there. How'd I do? Did I cover all the bases, Kurt?
Yeah.
Okay, good. Well, please let me know if you have questions and I'll hang out a little longer in case someone does.
Are there any questions? Okay.
No? Okay. All right. Thank you.
Thank you, Elizabeth.
Yeah, thank you. For
You're
what it's worth, I had no opportunity like that when I was in undergrad, and would have loved it.
Well, it is amazing how many students because I've been working in this field since 2008. And what is remarkable to me is out of every cohort, every workshop, every competition, there's one student or two that stand out. And it's been extraordinary to watch how their careers have unfolded and how these conference experiences can be very transformative and how they shape what it is they want to do in the future, who they meet. And it usually comes down to the people, because the skills that we train may change. Things are changing really rapidly, but the people you meet, the relationships you make are with you for their lifetime. So I encourage everyone to come and make the most of it.
Awesome. Thanks again.
Thank you.
Okay, so we could switch over to the VJs, I think.
Yeah, okay. And the pizza is on the way
Oh, it is.
in the next, between 15 and 40 minutes. We'll see.
You want us to meet them at the door?
They'll text me. So
Okay.
yeah. All right, let me make sure.
Okay. Should I just start?
You're good to go.
All right. Hi, everybody. I'm Vijay. Most of the people in the UHPC are new, so you probably don't know me, but back in the day, we started the club after the glorious days of the UHPC when things were going down a little bit, and then Ben came on, and then the rest is history, so you heard about that. These days, I'm kind of a washed up HPC person doing my PhD at Georgia Tech. And in the past, I used to do these things called HPC Roundups, where I would talk about what's happening in the industry, mostly from the perspective of compute. And I'm back to do that once again in person. And these have been really fun in the past. There's a bit.ly link at the top if you'd like to follow along or reference these slides. But with that, before I get started, I just want to make a disclosure. I do have a full-time employer right now that is not Georgia Tech, and I'm just going to say this has nothing to do with them. These are my opinions. I have a CYA a little bit, so that's the disclaimer. Second disclaimer is also that if you do happen to work at any of the companies or products or whatever that I'm going to talk about, please don't take this personal. I like to meme around, and some of them are just mostly jokes. If I'm wrong, let me know. Anyway, I'm mostly going to talk about Hopper today, which is the new GPU that NVIDIA announced a few weeks ago. And then I'm also going to cover some hardware news. The last time I did this was about 2 years ago, so I'm probably sure that I missed a lot of stuff, but such is life. But with that, let's just dive straight into Hopper. So kind of want to do a poll of people who've written GPU programs before, because I've sort of just realized that most of the people who have. Okay. Very few, so I'll please ask questions. don't feel intimidated. We need more people to write GPU programs. So if you don't know anything or don't understand it, please feel free to interrupt and poke me about it. But for those who haven't written GPU programs before, this will be a good summary of the white paper that NVIDIA has published. But I would highly recommend that you go read the Hopper white paper if you want more details. That's the picture of the chip. It's quite large.
Just how large, I'll put it into perspective. This is the last generation chip was A100, which was about 826 millimeters square on TSMC 7 nanometer. This one is 814 millimeters square on TSMC 4 nanometer. So the chip size remains about the same, but transistor density like gets like 2.5x or whatever. So it's quite a large chip. It's about 80 billion transistors or something as compared to 40-ish, 4100. The main changes are that the TDP goes from like 450 or 500 watts to all the way to 700, quite a large jump. I don't know how you guys are going to cool these things. They're pretty rough. Anyway, the SM count goes from 84 or some, 108 to 132. So only a sizable increase in the number of cores. By the way, for the people who don't know what SM is, on CPUs you have cores, on GPUs the core equivalent will be the SM. So instead of 108 of them, you have 132 cores. Now, shiny new thing, HBM3. We haven't seen HBM3 before. HBM3 is the new standard high bandwidth memory. And this thing has 5 stacks of it at 80 gigabytes storage capacity. And the bandwidth is a massive 3 terabytes. So A100 was about 1.8 terabytes a second for context. L1 slash shared memory size goes from 192K to 256 kilobytes, which is like a 33% increase, so fairly substantial. And the L2 also increases to 50 megabytes instead of 40 or something. The really large increase also comes from the off-chip bandwidth. So instead of 600 gigabytes off-chip bandwidth, we now have 900. And of course, the teraflops go up correspondingly. Now, what's interesting is that even though the SM count only goes up by like about 25%-ish, the throughput of floating point compute, at least in terms of tensor cores, goes up by almost 3x. And how that happens, I'm going to go a little bit into it as well. And that mainly comes from pretty big microarchitectural changes. So UARCH is an abbreviation for microarchitecture, for the uninitiated. And Volta to Ampere was a fairly conservative microarchitecture change. This one is a massive, massive microarchitecture change. And I'm going to go a little bit more into the main ones. The main ones are TMA, DPX, thread block clusters, distributed shared memory, and FPA. And now I'm going to break down all of those one by one. So in terms of a little bit of a refresher, Ampere introduced this one unique microarchitecture feature, which was asynchronous loads from global memory to shared memory. So shared memory is your local scratch pad, global memory is your VRAM, the normal system memory that you have on GPU. What used to happen in the past before Ampere was that whenever you loaded data, you would need to stage it through registers, and then it would go to shared memory. So you would have registers that are tied up doing loads and stores. They're not doing anything useful in terms of computer. With Ampere, you could issue loads that would go directly from global memory to shared memory, and that would free up some registers for you, and also they were asynchronous, so you could do deeper software pipelines with it. Hopper takes this to a new extreme and creates an entire asynchronous machine out of it, which lets you do the same kind of deep software pipelines, and lets you issue like data movement instructions and like which are simultaneous with your math, but also introduces a new thing called a transaction variable. So instead of just counting number of threads that are arriving, it also counts the bytes of data that are moved together. And what that lets you do is do something called TMA. Now, TMA instructions, as opposed to like the old Ampere LDGSCS stuff, lets you move tens of kilobytes of data with a single instruction, rather than like as compared to like LDGSCS. So like each SM has 128 threads that you need to fully occupy it for execution, right? And if you were to issue the largest possible LDGSCS, which is 128 bits, at most you'd be able to move 2 kilobytes. So that's 128 threads moving 2 kilobytes at a time. Now with TMA, a single thread can move tens of kilobytes at a time. And what that lets you do is that this is asynchronous, right? So you can be executing important stuff on the threads while data movement is happening automatically in the background. So it's like if you're familiar with DMA, it's like a DMA at the level of instructions. You can do DMA to global memories, pretty much. It also accelerates the other way around, so you can do stores to global memory with DMA as well, and it also supports reductions. So reductions are going to like sum up a bunch of stuff in a vector together, and TMA can do that for you as you're performing the main data movement as well. What's really cool for a programmer though, so if you're writing GPU programs, usually the hardest part of writing GPU programs is managing the thread to data mapping, what threads own what data. What TMA does is it takes care of a lot of this for you. So usually you have to compute like what accesses are out of bounds and then predicate them away so that you don't like seg fault on some load that's out of bounds and stuff. You also need to do predication and handle corner cases like that. You also, of course, need to generate the addresses that you're going to issue the load and source for. TMA takes care of all of that. You don't need to do any of the address generation math. You don't need to handle any of the corner cases or predication. It'll automatically pad accesses if they're out of bounds for you, which is really, really cool. This massively reduces the number of instructions that you need to issue. And more importantly, personally to me, it massively reduces your mental overhead of writing GPU programs. You just say, here's my tensor, up to 5 dimensions large in extent, and I want to load this coordinate with like 32 elements y, and it'll take care of everything for you. And then with the barrier stuff, you can just wait on it until all the transactions are. So that's pretty cool stuff. TMA is a pretty interesting instruction set. What comes with it is also thread block clusters. So if you've written any CUDA before, you're familiar with the concept of grids and then thread blocks and then threads. Grid is a bunch of thread blocks, thread block is a bunch of threads. Now, it turns out GPUs have gotten so large that a thread block by itself isn't a large enough granularity at which you can express locality. So Hopper also introduces a level between the grid and the thread block. So the thread block is a collection of threads, and a grid is a collection of thread blocks. But now with thread block clusters, each cluster is a collection of thread blocks. Now, what does that buy you? Like, how is that helpful at all? Well, the hardware has some pretty interesting features for thread block clusters. It supports faster synchronization, and more importantly, it guarantees that all of the thread blocks. So usually you can think about thread blocks as a single thread on a CPU. So whenever you issue multi-threaded programs on a CPU, you have no guarantee for what threads are going to execute on what core and stuff. What happens over here is that with clusters, you are guaranteed co-execution of thread blocks which are within that cluster. And what that buys you is that if you know they're executing at the same time, they can operate on the same set of data so that you can produce data movement and you get execution efficiency out of that because you have more locality. One of the fundamental principles of computer science, right? Like caches and memory hierarchy. The more stuff you can keep local, the faster you can access it and the more bandwidth you have. So clusters allow you faster access to larger localities that you can now express in software. There's also a dedicated network on chip that connects SMs that execute a cluster together. So again, for more precise technical terminology, all of the thread blocks execute on a single GPC. And what that means is like it's a hierarchy of the chip where they're physically on the silicon closer together, so that your accesses take much shorter time because there's a delay of like electricity transport on the chip. It's pretty cool. So this lets you express that in your C++ code when you program the GPU itself. And that also enables the next really cool feature. So until now, when you had shared memory, which is your accessible cache per core, you were only limited to the one thread block that it could see, right? Now, if you have a cluster of thread blocks, they can actually access each other's shared memory in other cores. So you can grow the capacity of your shared memory across SMs. So you can pool SMs together and then access their own shared memory by just dereferencing pointers. It's the same old interface. You just map the remote SM's shared memory space into your virtual addresses. It works just like normal pointers would, and you just access it like you normally would as well. With the benefit being that these accesses can be asynchronous. And the TMA thing that I talked about earlier can also access the shared memory of your sister SMs within the cluster. It also supports much faster synchronization. There's a cluster sync support as well. So you can build hierarchical parallelism this way, like starting at your threads, then thread blocks, clusters, and grids. So this adds a very, very nice hierarchy extension. Of course, there are tensor core enhancements. This is one of the really big microarchitecture changes in Hopper as well. So as you saw, SM count went from 102 to 130 or something, but A100 was 360 or something teraflops at FP16. This thing by itself is 1 petaflop of FP16 per chip. So that's a 3x increase in compute power. And that mostly comes from enhancements to the tensor core itself. There's also a new tensor core instruction set extension, which now supports floating point 8 data types, which is kind of mind blowing actually. 8 bits as a data type for floating point is kind of wacky. And what's really cool is that it's not just a single FP8 data type. There's 2 different forms of FP. You can have either 5 bits in the exponent and 2 in the mantis, or you can have 4 in the exponent and 3 in the mantis. So you can pick between the 2. It's pretty cool. If you have the right programs for these, that's going to be a wild ride. It'll be pretty interesting. There's some stuff that I'm not covering here. There's stuff that uses FP8 for transformers specifically. So transformers are a class of neural networks usually used for very, very large language models and computer vision models and stuff. There's a software package together with this tensor core instruction set that will like automatically adapt the precision of your compute based on how much you need. So it'll start off with FP8 so you get the higher performance, but then if it needs more precision, it can go to BF16 or TF32 or whatever it is. So there's some cool stuff here, but man, this is a chunker of a chip if you are doing a lot of matrix multiplies. 1 petaflop of FP16 is pretty crazy. It is also 500 teraflops of TF32. So TF32 is like a reduced precision FP32. For FP64, I believe it's like 60 teraflops for matrix multiply, but of course that's going to be much smaller. By the way, this is a great way to visualize these as well. Tensor cores are split along each subpartition of the SM. So if you dig into the NSM, it's kind of like a CPU core where you have 4 vector lanes, like 4 SIMD units, and each of these 4 makes up the one subpartition of the SM, and they're doing their own matrix multiplies in parallel. So there's a pretty good mental model of how it works. So how does this build up together? Well, you combine 8 of these Hopper chips together, and that becomes the H100 HGX board. You can kind of start seeing how this thing is cool. Like, look at that slab of copper over there. It almost looks like a centimeter thick. These are, of course, water cooled, but you cannot possibly air cool a 700-watt GPU. It just will explode and light your server on fire. But yeah, this thing together is like 32 petaflops of FP8. And for normal, like conventional HPC, it's 480 teraflops of FP64. Whew, boy. This one also has in-network computing. So like the new ND switch also supports Sharp style in-network stuff. So whenever you're doing like MPI, whenever you're writing MPI programs, you'll sometimes have like all-to-all reductions and stuff. And the network, in this case, can actually accelerate those reductions while you're moving the data itself. So you're computing the reduction as you're moving the data itself. So it offloads that compute off of the GPU into the network itself. So let's scale it up even more. How do we build a supercomputer out of this thing? So in the past, you would like connect all of these together with like infinite band or whatever, which is the traditional data center HPC way of doing things. Hopper also has a sister chip with it, which is the ND-Link switch. So ND-Link used to be only for 8 GPUs at a time. Now it's extended to an entire superpod. So superpod is 256 of these H100s strung together with ND-Link. So that's 32 HGX nodes. And there's some pretty huge upgrades to be had from here. So A100 used to have like 6,400 megabytes per second of like bisection bandwidth. This thing has like 57 terabytes per second of bisection bandwidth, which is like a 9 times upgrade. Pretty sizable 1 generation upgrade in bandwidth. And of course, with that also comes the in-network computing stuff. So you get 4.5% reduction bandwidth gains from that as well. It's a pretty huge networking upgrade for connecting these GPUs together. And kind of like the takeaway point from here, like if you don't care about the microarchitecture at all, know that even though if the chips are getting much more powerful, for the workloads that we're running today, you kind of need to scale out. There is no way you can build a chip that is physically large enough to do everything that you want to do. And the only way to scale up is if you have a lot of interchip bandwidth. And for that, you kind of need a 9 times upgrade in bisection. Otherwise, how are you going to communicate with each other? The more and more these GPUs get faster, the more and more you need to move data to feed them in the first place. If you don't have to feed them, all the petaflops are going to be completely wasted, right? So like you got to do something to move data around, and that's this. NVIDIA is already building a supercomputer out of this. So this was one superpod with 256 GPUs. 18 of them together, which is 4,600 GPUs, is going to be the NVIDIA EL supercomputer with like these specs. Specs are less interesting than what we're going to use it for. This is mostly going to be used for climate modeling and traditional HPC applications, as well as training NVIDIA's own AI models and stuff. It might be the largest supercomputer owned by a private company when it's built, I think. Pretty interesting. There's also a really interesting version of this. So A100 had this as well, where there was an A100 chip on a networking card. This is kind of like carrying forward that legacy. This is an H100 on a Connect 7 Mellanox network card. So instead of having a CPU, which your GPU plugs into with PCIe, now your network card itself runs the entire OS and hosts the GPU on the networking card itself. So you don't really need to have a host system or anything. You just have a server bucket full of a bunch of Bs, and then somebody like AWS can actually provision GPUs that are not even in your system. They're connected over the network with a 400 gig link, because these NICs are 400 gigabit per second. So like you have a lot of bandwidth that goes off of the NIC itself, and you can RDMA between the memory of the like anything on the network with the GPU memory. So you don't need to ever go to another host CPU at all. There is no host. This thing is self-contained. Pretty cool. So you kind of have like an accelerated GPU system with a 2U like networking card. Pretty interesting. I don't know who uses these, but I'd be curious to know. They also announced a CPU package with it. So NVIDIA is building their own CPUs. This was announced last year originally, but they reiterated that, where a single board has a H100 and a Grace CPU complex attached together over a very, very high bandwidth link. So the link is 900 gigabytes per second, so all basically the same bandwidth as NVLink. What this lets you do is like traditional PCIe Gen 5 will be about 128 gigabytes per second. So this increases that by another 8 times, so that you have a much faster link between the CPU and the GPU. Now what this means is your GPU is no longer limited to 80 gigabytes. You can entirely access all of the system memory on the CPU side as well. And of course, they stick 2 of the CPU complexes together for a massive 144 core CPU as well. I'm a GPU programmer, so this is somewhat less interesting to me. Anyway, that's it with the NVIDIA news. Questions so far? Anybody? Yes?
Any benchmarks released from any of that?
Not yet, I think. I didn't really pour over the keynote and stuff too much, but maybe there's some around. But yeah, I'm not aware of any benchmarks that are available. We shall find out.
Since they both share the same memory, you don't need to mem copy anymore.
Nope, it's coherent. It's the same virtual address space.
So when you I typically, CUDA malloc all the device on the card, and I divvy up who gets what, right? So you don't even have to do that. How do you get the pointer to the GPU memory then?
It's all unified memory. So you can do CUDA malloc managed these days as well, which would give you a pointer that you can reference both on the host side and the device side. This would be an extension.
Oh, okay.
Yeah. So you just allocate memory with managed. The driver handles. So these days, driver handles it. In this case, it's hardware accelerated coherency, so you wouldn't even have to have the driver handle any kind of page fault or anything.
So if I had 32 gig and I wanted to use 16 for my GPU app, I could CUDA malloc manage 16 gig,
yeah,
and let the OS or the runtime handle
everything.
CPU memory for its usage.
Yeah, absolutely.
Nice.
And you can do that today as well. This will just be accelerated version of that. So you just see transparent gains in bandwidth pretty much. Now there is a downside, of course. Like HBM3 is still 3 terabytes per second, whereas if you were to go to the CPU, you were limited by the link bandwidth of 900. So there is about a 3x difference there. But it makes GPU programming a lot more accessible. Right? Like you no longer have to manage the transfers between the CPU and the GPU. So like if I'm just writing standard C++ and I suddenly want to like make it go faster using the GPU, you can do that. This is the programming model story for coherent managed memory is a lot stronger than the actual performance story. The performance of like manually doing what you do is of course going to be better, but that's considered more of a ninja programmer way of like, if you really knew how the hardware works, right? Like if I just want to make a vector add work, you can just malloc manage and let the GPU do it.
Does NVIDIA have a DGX equivalent where it's HBM3 to the CPU as well?
I'm not sure. I am not aware, and I cannot speculate anymore because in my current folder.
So I see NVIDIA coming out with their own laptops. Now they got this Grace, right?
Yeah.
They always relied on other vendors for their CPUs. Now they said, forget it, we're doing our own. That's what they did with it. They said PCIe wasn't fast enough. They did NVLink. So
That's right.
they said the CPU isn't good enough. We did our own. Now you're going to see NVIDIA boxes coming out, right?
Yeah.
And they're going to be taking over this whole market.
No comments.
Right? Don't you think so?
I used to speculate a lot on what future roadmaps would look like, and I would cover geeks as well, but like now I'm in the industry, I can't really do that. So I will let you all speculate as to what NVIDIA roadmaps hold and do not hold.
Are there some techs now that are obsolete? I mean, do we have a new programming paradigm for DNA and we just bail on it? Well, so now you had a slide where it was less of a mem copy, it was more of a pointer. So that
Oh, so that's for the shared memory stuff, right? This is what I'm talking about?
Yeah.
So this is the shared memory pointer. So this is on the device when you're writing a device code within the kernel itself. You can map the shared memory of your neighboring SM to your shared memory as well. So you're no longer limited to like a single SM's capacity worth of shared memory.
okay.
All the SM, well, technically all the thread blocks within a cluster have a pooled shared memory size. So let's say my cluster has 4 thread blocks in it. I can access up to 1 megabyte of shared memory within my kernel because 256 times. So it basically lets you have even more capacity for low latency access for your structure. The other one was the CUDA malloc manage, which is the system memory side, because that global memory. So like we ran.
So if I read a lot of CUDA stuff. If I take the thread blocks and I create clusters out of it, just do that. Should I see a speed up without getting involved?
You can, depending on what your code is actually doing. So clusters are guaranteed to co-execute, right? So let's say all your clusters are accessing the same section of global memory. Then, well, you will access the same lines in global memory, and the L2 will cache it. And since they're executing at the same time, all of them, the first one will miss an L2, but all the rest of the CTAs in the cluster will hit an L2. So you can have a lot of bandwidth savings depending on what your code is doing if you just create clusters out of your existing CUDA code engine documents.
Yeah, because I use image processing, right? So I access this piece and it's coalesced. So I'm basically going down the line. So if I take one thread block and pair with another one,
yes, you should be
that
able
should speed it up, right?
Yeah, you should have a higher hit rate in L2, which should hopefully translate to a higher performance.
Okay.
Yeah. But again, it's completely code dependent. Like it depends on what your application is doing, but it seems like this is.
When you say coalescing, you mean it's caching or
It's taking, instead of randomly pointing to various elements of an array, you know, thrashing through the memory thrashing, it's using, you know, ace of I is, you know, the first one, the next one, the next one. So when I process an array, I'm not, ace of I is pointing to the first one, and then ace of 2 is the next one. Is, you know, it's like when I reference an element of array, I'm not pointing to, I'm processing in sequential order, you would say. When I do a 2D image processing, I process, you know, in fast time dimension.
Yep.
And I'm not poking around, which is. So I was just wondering if I did that. It sounds like I would.
Well, as long as your different CTAs are accessing the same memory, if you put them together, then they'll have more L2 bits. So in that case, it'd be helpful. But if you're only accessing every element once, you're still down by the global memory. So, again, it would depend on the application, but it sounds like it. I know for matrix multiply this way, right? Because you have the same tile that gets loaded from the A matrix and the B matrix and gets reused across a bunch of different CTAs. So in that case, this will help. Okay.
I got a high-level question.
Yeah.
So the fact that these are water cooled,
Yes.
how much of a barrier is that for like medium budget HPC customers?
Elliot's a perfect
There are
person to
other
answer that.
options. Yeah, so that big sled is the big option. There will be things that look like cards. They'll consume fewer watts. So I work for a company called Micro. We actually did a presentation at GTC this year about how much you can shave power without losing performance. And sometimes it's fairly significant. Like you can cut half the wattage and some apps don't even notice the difference. It varies a lot, but
You're saying when you use water cooling?
with even air cooling,
Yeah.
sometimes you can cut the wattage without hurting performance, or you cut the wattage by 50% and you only lose 10% of the performance or something like that. Sometimes it's a very nonlinear trade-off.
And so doing that, it would still be cost effective to buy these?
Yes.
cards?
I mean, you have to have, I don't know, how many operations do you have to need a GPU these days? It used to be like you needed to do at least 1 million ops, I think, to get a GPU. Now I don't even know.
So I read an amazing blog post by a person who works at like a AI, like OpenAI, and they wrote a post about conceptual mindset around GPU programming. Why would you want to use it instead? And they were saying, they were taking Python as an example. Like, let's say you have an array of floating point numbers in Python, and you're iterating over it and then adding them all together. In the time it takes Python and that entire abstraction to do one addition, this thing, Ampere actually, so the version before this, it can do about 1 million flops in the same amount of time. So if you 3x it for Hopper, it would be about 3 million floating point operations for Hopper, right? So usually you use GPUs for where you absolutely need blazing fast performance, or if your data set sizes warrant that, right? This, I'm kind of covering the Lamborghini version of what this would be. There is a Porsche version of this as well, which is the PCIe version, which is only air cooled. So they're both extremely fast, but this is up to 700 watts. The air cooled version is up to 450 or 500. I forget what it is, but you can read the data sheets and stuff. So there is definitely an air cooled version of H100 as well. What's really interesting though is the water cooled version has HBM3. The air cooled version has HBM2E, which is the same version that Ampere uses. So you're not as fast, so you need less bandwidth, so you can use the previous version instead. But yeah, there are definitely like smaller versions of this as well. As for economics, most of the people who are buying this have a lot of money. Yeah. But yeah, again, like I think the takeaway message for like at least the undergrads in the room is hierarchical parallelism. If you want to go fast these days, you need to think about data and execution locality and how it's going to map to your hierarchy of the hardware. Like, because writing, like, in the 70s and 80s, you could have written a CPU program and pretty much guaranteed that it would get faster every year, over and over again. We don't have Moore's law anymore by our side, so like, you got to get clever with writing code and scaling out, and that's why HPC is important, because distributed computing is like a pretty fundamental part of it. Okay. Any more questions about the NVIDIA stuff? Elliot's going to cover more of the software side and other products that NVIDIA announced, but I'll move on to other hardware things if there's no more questions. Okay. AMD also announced, this is slightly old, but AMD also announced their new data center GPU card, which is MI250X. Now, if you remember MI100, I covered that about 2 years ago. MI250X is basically two of them fusioned together. Pretty much. And what that translates into is this picture. Like you can literally see two of them together. You have 8 stacks of HBM now, so it's a lot of capacity. You have 128 gigabytes of memory at 3.2 terabytes per second. And this thing is also extremely powerful. It's 560 watts, PCIe Gen 4 still. And you can see the speeds. This is what Frontier has, by the way. Frontier is supposed to be the largest exascale supercomputer in the US. At Oak Ridge. Hopefully we see that at SC this year. But yeah, another GPU from AMD. Intel also announced a new core, finally. Took them forever. But this is Golden Cove. Golden Cove is quite the huge core. It's quite the chungus. It has a 6-way decode, which is the first for an x86 core. It's pretty hard to do decode in x86 because instructions can be 1 billion bytes long, pretty much. So this is pretty cool. It's a really cool core. It's just that it's huge, like, and not just huge in terms of its specs, it's huge in terms of its area as well. This thing takes up a lot of silicon. And you can kind of see the specs over here. They beefed up the cache, the load ports are larger, there's more bandwidth, higher ROM size, blah, blah, blah. There's a 5th integer port, which Intel hasn't done in forever. So it's kind of a pretty big change microarchitecturally. And it all translates into like about a 20% speed up over the previous generation core, which was isolate. And now covered isolation capacity. This also includes the AMX technology that Intel talked about here. AMX is their CPU version of a tensor core, essentially. And you can refer to the past Meetup slides if you want to know about that.
Do you know what numerical representations those companies do? Does everybody have B-float now?
So Intel only does FP16 and Int8. They do not have B-float for AMX. And I could be wrong, but I think they only have Int8 and FP16. I'm sure some future version will contain B-float. Like it's the whole industry seems to have settled on BF16 as like the standard format for the default machine learning data. But I don't think it does right now. They also announced a new little core, and this is actually honestly way more interesting to me than the big core. This new little core has something really interesting. Usually the decode will focus on a certain amount of instruction width. So like it'll try to decode 32 bytes at a time or something like that. Golden Code, for example, this thing tries to decode 6 instructions at a time, right? This thing is pretty cool. It'll try to decode from 2 separate fetch windows. So like it could be completely different parts of the code that are being decoded, each 16 bytes or less. And it can decode 6 instructions still, but it's a double decoder, each decoding 3 instructions at a time. And it's really cool because if you take a computer architecture course, you'll know that when you're doing decode, you're running ahead of your program. You're trying to speculate your decodes, right? So what this allows them to do is follow a branch and not follow a branch at the same time, and still do decodes of both ends at the same time. And it would significantly reduce your misspeculation penalty. It's pretty cool. And it's a huge performance win. This actually pays off pretty well for them. So Skylake, if you ever built a gaming PC in the last 10 years, it's probably Skylake. This thing is about 2.5 times faster than Skylake while being smaller and consuming less power. So it's a tiny little thing that packs a lot of power. It's pretty cool. And you can read more about it in the links. All of these have links at the bottom. You can follow them and read them through them. GraphCore, ML people. It seems like a lot of the compute progress is coming from the ML folks at this point. They're ready for Vijay as well. And GraphCore talked about a pretty new cool technology. Normally, I haven't really covered it, but they did something new with their IPU stuff. So they call IPU, which is their product for Intelligence Processing Unit. Boy, but strong marketing name. But this thing actually demonstrates a new fabrication technology, and I used to cover fabrication technologies a lot in the past, so kind of wanted to pay homage to that, which is TSMC's wafer on chip stacking. No, wafer on wafer stacking. So whenever you build chips, right, you have a large 12-inch plate-sized silicon wafer, and you dice it up, and then you make dies out of it, right? What this does is they actually stack dies on top of other dies as like a whole wafer. So you take one wafer where your IPUs are, you take another wafer with just capacitors on it. So it's deep trench capacitors. You make chips that only have capacitors on it to smooth out power delivery. And then you literally stack the 2 wafers together so that the actual processing unit has smoother power delivery. And what they were able to do is get 40% faster clock speeds from having better power delivery. So it's pretty cool stuff. Just same processor, nothing changed architecturally. You slap some capacitors on it and it gets 40% faster.
For someone who knows nothing about this technology, are the clock speeds applicable to something I'm familiar with, like a 3 gigahertz CPU or something?
It's roughly in the same ballpark. So
Yeah.
it goes from like 2 gigahertz to 2.8.
Okay.
Something like that. But it is in the gigahertz.
And these GraphCore chips are on PCI cards.
Yes, they are on PCI.
Okay, so that's going to be the limiting factor. You're not going to
Interesting.
crazy megahertz out of PCI card.
This is at the same speed, the same power. No power increase 40% faster. It all comes from just the transients. Your transient load for a lot of these matrix multiply units and FMA is going to be pretty harsh. So you sometimes have to like conservatively clock these so that you don't like trip up over current protection thing on the board. So if you have capacitors that are on much closer to the chip, you can have much smoother power delivery. So at the same thing, you can increase your clock speeds a lot. That's my understanding. But again, there's a lot more information you can find if you want to read about it. That's the link right there. They also announced the good computer. My God.
That's not promising too much.
Man, it's so weird. Okay, I'm gonna save my opinion. Grab me at a bar if you want to. But yeah, this is painful marketing. Jesus. They are not building this, unlike NVIDIA, as far as I know. But they said that they can build this for you if you have a spare $120 million burning hole. Show me the software. That's my message. But yeah, it's cool. It's cool. It's cool. I'm hating on them too much. It's cool. They can string together a lot of these Mark II Colossus IPs, 8,192 of them together to build a supercomputer. And again, same thing comes up, right? A single IPU, no matter if you build the accelerator just for machine learning, it's not very good enough. You gotta go wider. You gotta scale up. You gotta scale out somehow. No matter how much you scale up, you gotta go wider. And for that, you need great off-chip bandwidth and a great distributed software support. 120 million isn't horrible. That should be fairly cost competitive. Who knows? Now, elephant in the room. Tesla Dojo. I have lost count of how many people have asked me about this. So I'm not even talking. It's not going to invent AGI. Calm down. I know Elon Musk has a lot of hype around it, and this thing is cool. I'll give you that. But there's a lot of reason to be skeptical about it. Anyway, let me go over what it actually is, right? So what they've done is actually very similar to Cerebras, and I've covered Cerebras in the past, which is a wafer scale machine learning processor. What they've done instead is use another TSMC breakthrough technology. TSMC, by the way, for the uninitiated, basically makes every single chip you've ever used, and will continue to do so for the foreseeable future, it seems. Anyway, so TSMC has this new technology called Info Wafer on Substrate, I believe, is what WOS stands for. But info is integrated fan out, and fan out is a very complicated way of saying, how do I connect wires between two chips together? So wafer on substrate tells you that they have an entire PCB where they can put an entire wafer on it and then connect it up together. That's what Info WOS is. And that's what Tesla people are using to basically build a wafer scale processor that is not actually wafer scale like Cerebras is. So Cerebras takes an entire wafer and then truly is a wafer scale engine, whereas this one takes the same number of chips as would be on a wafer and then puts it on a carrier like substrate with the Info WOS stacking technology. And there's 25 of them. Each die in the Dojo processor is about the same ballpark as an A100. And then there's no DRAM at all. So there's no HBM, there's no memory. You only get SRAM, which is your caches. So there's only on-chip caches, nothing else. Again, exactly like Cerebras. Neural networks are then mapped onto the compute and fabric at compile time, exactly like Cerebras. That's what they do as well. And this also supports FP8. And guess what? They also call it configurable FP8. If I had to take a guess, it's pretty much the same kind of exponent and mantis of bit trade-off. But I'm not sure. I don't know what Tesla does. But if I had to guess, it's probably the same. It looks really cool. I watched this thing live. It was pretty awesome. They did a pretty good job of like presenting it to people as a marketing tool. But it is really cool technology as well. This module also looks pretty similar to Cerebras' stuff if you've seen it. Note the even more copious amount of copper on this thing.
So that was almost a life-size photo.
So these are yay tall, yay large. And each one is about 18 kilowatts.
And it costs $1 million,
I
$1
don't
billion
know.
bucks.
So that's the, okay, so I was gonna come to the end of it, but
Oh,
for people who are interested in the economics and business side of building chips, you don't just tape out a chip. You don't especially just tape out a chip on TSMC 7 nanometer. And on top of that, you don't just front run a bleeding edge technology from TSMC. This stuff costs a lot of money, a lot of money. And I don't know how they're ever breaking even on this, because in order to actually ever make a profit, you need to sell millions and millions of chips. And they're only just building one computer. So if you're designing your entire chip, and not just that, your entire system is custom because this thing isn't standard at all, how are they ever going to make their money back? I don't know why they're doing this. And this is already like a Hopper cluster is already going to meet this and like put it into the What are they doing? I'm not sure. I don't get it. I don't get it. For the people who think that Tesla is gonna like save money by doing this, that's absolutely not true. You need to hire people, hundreds of them, to build and design this chip. You need to write all the software from ground up. You need to qualify it. You need to make sure it goes fast, because what's the point of building your own hardware if it doesn't work fast? It could work, but if it doesn't work fast, what's the point? And even then, you're only gonna like, they say they're gonna build a cluster that is, I believe they're gonna build a cluster that is about 1,000 of these, roughly, on the order. 100 seems too little, 10,000 seems too many. About 1,000 of them, which is what? 1,000 times 25 is 25,000 dies.
What market are they gonna go after?
I don't know. I don't understand this. I don't know what they're doing. But it's cool. It's cool technology, so I'm happy. Anyway, it's actually, again, the similarities with Cerebras continue even more. So Cerebras had a north, south, east, west fabric, and at each intersection point you had one small little core with a vector unit on. Same story again. You have a NFC router, so that's your fabric on the chip, north, south, east, west. And then each one is one clock away, just like Cerebras. And then at each intersection, you have a RISC-V-ish core, where you have a vector processor that does all of your AI, FP, whatever, 8 multiply and stuff. And then you only have the SRAM, which is your on-chip cache. And it's a superscalar CPU. Very, very similar to Cerebras, actually. By the way, they say ISA optimized for ML kernels. That just means they have matrix multiply operations. Yeah, I really dislike Tesla marketing. They hype things up a little too much, but you could probably say the same about any company. Again, each chip is about roughly on the order of performance of the A100, but it is 400 watts as well by itself. Pretty chunker of a chip. What they're really focused on, as opposed to A100 though, is the off-chip bandwidth. And again, this goes to the scale-out story. Rather than waste money and power and stuff on HBM, they just added a lot more networking stuff to it. So you have 10 terabit per second off-chip networking. 4 terabit per second per edge. So edge meaning north, south, east, west. So you have 16 terabyte per second off-chip bandwidth that goes to other chips. So that's also only possible. You wouldn't be able to do this without the TSMC Info WOS thing. You just wouldn't get the wire density and power optimization. Yeah, so this is the scale out story. Each like yellowish square over here is one entire Tesla. It's one die. It's D1 die, and then you have them configured in cabinets in an array of 3 by 2. So like 25 of them, 25 of them, 25 of them. Then another row of 75. That's your one cabinet, and then you just string them all together. It's cool. Probably never going to make your money back. Yeah, I don't know what their business story is. I don't know, but whatever. Intel, very interestingly, made a Bitcoin mining machine, which is odd. They built this accelerator, which is the okay. I'm going to speculate. I think what they did was their CPUs have SHA-256 acceleration. They took that IP, Control-C, Control-V across the entire die, and then strung all of them together over like UART or something, and then called it a Bitcoin mining machine, which is pretty cool. It's interesting. I have my ethical and moral problems with Bitcoin mining, but technologically speaking, it's interesting. It's a pretty tiny die. So like we've talked about Thomas dies until now, like 600 millimeters square per hour. This is tiny. It's this like what is 14 millimeters square, about the size of an index nail. And it has 75 of them on a board, and they promise 40 terahashes at 3,600 watts. This means nothing to me. I don't know what terahashes per watt usually are in terms of GPUs or CPUs, but it's cool. You can read more about it if you want. But apparently they're going to sell these to customers. Again, when you're the size of Intel, you really care. Like this is a pretty small business for them. They ship like 10 million CPUs a day. Other stuff. Ice Lake finally released. If you have known me, I have been talking about Ice Lake since 2017, and it kept getting delayed every year, and it finally released. And we can all just like forget about it pretty soon, hopefully. Well, it's not gonna happen. But anyway, Intel finally shipped a product. Hallelujah. Sapphire Rapids is their next CPU that's gonna follow up with Ice Lake. And they've said that this is going to be a CPU that has HDMI, which if you've heard of KNL before, Nice Landing, it's going to be pretty similar to that, I think, where you have very large, fewer larger cores that have access to much power bandwidth. So it's going to be a CPU that has HDMI. Aurora got delayed again, Aurora. That's their exascale supercomputer that was supposed to be at Argonne. If you remember, and you go into the annals of HPC, it was originally supposed to be A18 with the successor to Nice Landing, but that got canceled, then delayed by 3 years. And then it was A21, and we are in 2022 now, and that is not 2021. So, yay. Ponte Vecchio is the GPU that's going to be in the Aurora machine. And I attended Hot Chips in August, and I don't think they intended to do that, but they slipped out something, which is that they will not support CXL. They've been talking about hardware coherency. Well, they never said, they were very clever about it. They never mentioned hardware coherency, but they mentioned coherent memory, which is the thing that I was talking about earlier. The CPU can access the GPU's memory without any extra work that you need to do. Apparently, it doesn't support that. Fantastic. Great. I don't know what they're doing.
And you're saying all their competitors do that.
Well, so with Grace and Hopper, you can have hardware coherent access between the CPU and the GPU. And AMD has been saying that with their MI200 and whatever future GPU, you have Infinity Fabric that also lets you do the same. So Intel doesn't really have a product that can support that. Well, they have the protocol and everything. It's just that the implementation of the IP doesn't really support it. Which is lame. Like they're the ones who made CXL. Like, where you guys are, it's like they had a lead on CXL because they invented the spec, but then their products didn't support it. I don't get it. ARM v9 was also announced and finally released. With that comes a new core. And v9 is pretty cool. It makes SVE, which is the vector instruction set, the baseline for everything now, and 64-bit only. So that's that. Anyway, let's get into some process nodes and geopolitics. I usually end with this stuff because I find it pretty interesting. Process nodes are kind of stagnant right now. We should get 3 nanometer soon, hopefully. But I have decided that I will no longer choose to go into geopolitics because it gets pretty messy real quick. Again, grab me at a bar, we can have a chat. And that's it. So thank you. As usual, I will leave you all with a very, very hyper niche theme that most likely nobody will understand. We have audio.
Oh no.
I got you, yeah. 1 second. Oh no, the feedback.
Oh, yeah.
Yeah, Intel's been doing a lot of Zeta scale marketing.
Things. Yes, okay. Okay, okay.
So you guys want to go get some pizza, bring it in here, we'll go set up.
Somebody carry that or?
Oh, no, no.
Oh,
yeah. Grab a plate.
Gotcha, okay.
No. Oh, okay. All right. I'll go get some plates. I got some upstairs.
Yeah, you can grab.
Or you can just.
Yeah.
Oh, okay,
I
yeah.
don't think anybody's coming in, but.
I don't know, and I don't have too much to go probably. I just talked about what happens during this interesting. Okay, so I'm Elliot Eshelman. I work for a company that builds HPC systems. Some of them are kind of like this. I mean, you can do other things. Let's talk a little bit about the software. I spend honestly more time on hardware than on software, but one of the reasons I'm doing this is I think sometimes the hardware goes into the software a little bit too much. I'm happy to get pushback on this, but this is what everyone's talking about. Oh, we're going to do like 1,000x or 1,000,000x over the next couple of years, when historically you get like 2x performance improvement every couple of years. So it seems like what is happening in practice is that the software is really where the speeds are coming from. And the big thing that NVIDIA is talking about right now is physics neural networks, which basically means like AI that understands physics. So it's a neural network that model physics ecosystems. It's actually been going on for a little while, it turns out. There's a couple of groups that have been doing this for a few years and getting good results. And the 1,000x speed up is seemingly realistic. Some folks are talking about 4,000x, 10,000x, 100,000x. So if you can get a really tight neural network that understands the particular physics that you're trying to do, it'll run a ton faster than traditional HPC. So traditionally, in HPC, like simulating the weather on a global scale, you need a giant supercomputer, even then your resolution is not that good. And run a much more accurate model on the same hardware, or you can run it much more quickly. So you can run it further out, or you can get results faster. This announcement that NVIDIA made is a digital twin. And if you're not familiar with the concept, it's been happening for a long time. And NASA coined the phrase. And if you're going to do something and you can't build it to test it, or it's too expensive to build it and test it, you do this. Everybody does this now, like you know, cans of soda are simulated on supercomputers, like diapers are simulated on supercomputers. Like tires, like everything, like I think cans of coffee. I heard of something, cans of coffee were leaking or something. Those were simulated. So it's just, you know, it used to be you had to build 10,000 or something and test it, break it, figure out how to approach, and now you just simulate on a computer, whatever that the models are. Sometimes it's fluids. That's one of the things that NVIDIA is going to do with this giant supercomputer building. Is they're trying to build a digital version of the Earth with all the weather systems and actually prove out climate change. That's something that the CEO talked about. Is they're going to demonstrate that here we are today, next year, year after year, and show people visually what the Earth is doing, and in the hopes that maybe that'll kick people ahead a little bit, honestly. And then this is the SDK. So NVIDIA's doing tons of software. Every time they're trying to do something new, they have an SDK for it. So this is the software kit for simulating a physical system instead of traditional HPC methods. And again, the speed ups can be fairly significant. Multiple orders of magnitude. And again, folks that have been doing this for a few years, they're used to 2x speed up every 2 years. So talking about 100x. The other thing is new ways to write parallel code. There's an increasing number of ways. If you've been doing GPUs for a while, you've probably heard about CUDA, that's for programming NVIDIA computers. Or maybe libraries, like instead of writing your own matrix multiplication methods, there's a library for all the common methods. Or directives, where you basically put comments in the code. So this is the parallel part, and then the compiler has to go parallel that correctly. But standard language is maybe I just haven't paid attention, but that was new to me. And C++ in particular. So C++ standards continue to develop, and now there are standard methods. So if you got a C++ compiler, you can write some code and you can run it in parallel. And for any like shell people, there's pipes. So I think that's very interesting because I come from the Linux world and it's very cool to be able to do that. It's very intuitive to me at least to be able to do that. Oh, this link, by the way, this link's and I'll share the slides. So I don't know if this is exciting in general folks, but it's exciting to me that you can write code the way you really want to write code, and then it doesn't just run on one core or one CPU. It doesn't just run on one CPU. It's running on multiple accelerators or CPUs in your system. It's also running across systems. So this standard C++ code is running on hundreds of GPUs, hundreds of systems, fabrics, like all the communications being done for you. And it's not linear, but it's pretty close. So this should be a big deal for people. I hope people get excited about this. There's already been quite a few different ways to program supercomputers, but being able to do it in a standard language is a big deal. So this is a really good presentation. People are starting to talk about it. I know it's linked before, but it's a presentation from GTC, so it's really good. And then this is kind of turning back to the digital twin. I've still been trying to wrap my head around this, but the best way I can think of it is simulating any real world scenario as a digital twin, like we were talking about before. And also almost like collaborative docs, like you've got Google Docs, multiple people editing at the same time, and they're doing that now for virtual worlds. And that's what Omniverse is for the video. It's connecting, you can see like physics, VR, you can just have internet access, connecting. Maybe you almost think of it like as a game engine for the actual world. They're going to build one that simulates the entire Earth, right? And also build one that simulates the factory. And they're pulling together all these different software packages. So I don't know if folks here have done like graphics or things like that. There's game engines, there's Photoshop, there are tools that are used by some of the top engineering firms in the world. So we bring all these kind of random things together, like the game engine and Photoshop and engineering software, and they can all work together. They do a lot. They can see changes live. And then there's also physics and rendering. So we're starting to see things where, yes, people can collaborate, but neural systems, AIs can collaborate too. So people will generate a virtual world, train their AIs in that virtual world. Instead of like training a car how to drive on the streets, which they can do, you can also get millions of hours of training in a virtual world. So I've seen similar things for robotics. I've seen similar things for traditional vision methods, where you're just teaching a computer how to understand what it's seeing. You don't have to put physical objects in front of a physical camera, teach an AI, you can do it virtually. So it's all kind of blue sky, big picture stuff, but I think that it's going to catch on. I'm starting to get the impression based on how many different folks are getting involved. Yeah, it's all over the place, anywhere from game companies, engineering companies, to folks doing business consulting. It's really all over the place. So it seems like people are buying into this. Multiverse is the other where you think of here. And there's a video. I know that's a couple of audio, but you can see people collaborating. So you have like multiple people remotely editing a scene, all seeing the same scene, making changes to it. Ray trace, whether you're on a tablet or system with a GPU in it. So it's potentially the future of digital twins and simulation model. Okay. Do look at GTC if you haven't, because there's a crazy amount of content. You can look at all past years as well as this year's. it's anything from like business people talking about AI, to coders like the C++ thing, to game designers. It's all over the place. Does anyone have questions? I'm not gonna answer you that fast.
I saw a digital twin demo where you're driving along and there's 17 cars out in front of you, and it's running ahead with the driver prediction scenarios.
Yeah.
So you've got this sort of like this flexible collision avoidance thing that's, it's kind of like how Watson rated things, you get a 19% chance of that red car taking a left turn. And so this multivariate stuff running super real time must be a spectacular amount there. Because if you've got, like, say you're on a highway, everybody goes 60. And some percentage of them are EVs or Teslas or something like that, so you can rate those down. But there's no crazy items coming out of a Tesla. But that would be pretty cool if you could get anything approximating real time. So if the car suddenly did an unusual behavior, it was because we had some of these negative scenarios coming up ahead.
My understanding is that right now in the test system, they basically have a supercomputer. I don't know. I think it's thousands of watts. I don't even think it's hundreds of watts. And they're talking about dozens of sensors per vehicle. So it is a serious amount of data that's happening. I don't follow that quite as closely, but it's embedded computing, but I don't know, embedded in hundreds of watts. Yeah, and I think as far as autonomous cars go, wasn't it like 2020 I don't know. We've been 5 years away from self-driving cars for a bit now.
It's like fusion.
Oh, well, I don't know. We're close to that. We got the physics and fundamental networks. I mean, what is iCar? I don't know. I don't follow that super closely. Well, my understanding is maybe a decade away. There's so much. Like, these are the other software announcements that I was able to find from this phone. Like, there's stuff going on all the time. From healthcare to like AI. Coded Python, there's now a replacement for NumPy. So like NumPy is what people use when we're doing that. And most of this stuff you can try for free. Like some of it's super enterprise, and you have to pay for it, get such and such. But if you're just a single user, most of this you can have it. So you can go mess with it.
Do you have any Jetson announcements?
There was some embedded stuff.
Is it more?
Is that specific for, I thought that was specific to autonomous driving, maybe not.
Well, they marketed towards the autonomous
But
driving,
anyone can have access to
but
it.
it's got a lot of horsepower. I was looking at
Is that the
the,
one that's like,
it's a box, yeah. If you go to jetsonhacks.com, the guy there, have you ever heard of him?
Oh, yeah.
Jim,
Yeah.
he's got a real nice one on the Orin, and he takes it all apart, shows you everything, tells you all about the connectors, and he runs this canned demo you can download from NGC, the cloud, and it's all AI stuff. But the specs on it look very interesting as far as being high performance in it, and for a 60-watt unit, it's got 2,048 cores. It's got a 2.2 gigahertz, 12-core ARM CPU thing. It's got 64 gigabytes of shared memory on it, DDR5. So it's not a bad little box.
Sure. In 2 days from now, Jetson's also getting rid of that.
Is that right?
It was supposed to be today, but they delayed it.
You usually try to stay a generation behind the big iron, but.
Well, the last update for Jetson was 10.2, which is quite ancient at this point. So yeah, it's like quite like 2 or 3 years, I think, right? 10.2. So 11.4 should be quite a hefty upgrade for all Jetsons everywhere. With that also comes C++ 14 and like everything else that comes with like all the new upgrades and stuff. Because Orin is Ampere based, so you'll get everything that comes with Ampere with the new Jetson product.
That was as hard to get as the Raspberry Pis and everything else. The last I looked, that's
No, they're sold out. I think they're even sold out in the company store.
yeah.
Yeah.
Now, Raspberry Pis are the same story.
I'm not sure, never touched
I
mine.
heard something. I guess everything's hard. You can't buy a refrigerator.
Micro Center does have GPU stuff.
Oh.
Yeah.
okay.
It's kind of surprising, actually.
Fine. Go get them tonight before they're sold out.
Yeah, right.
I get mine from the companies.
Okay, well, thanks so much. I hope this was good. I promised Elizabeth, who was talking before, that I would encourage you again to go to Pershing, because it's in Boston this
Yeah.
summer. It's getting really good.
Well, we'll talk at least once more at a BUHPC
Oh, yeah.
meeting, because, because that's the deadline. All coordinated with Deck and some of the other officers.
This is really good opportunities.
Yeah. Yeah.
Okay.
Great.
Once
Thank
again,
you all.
more
Yeah.
pizza. I don't know, grab a box on my head. Whatever. Nope, nothing else in the chat.